So, analyzing the graph of a function, and they list all of these concepts that we have talked about either last year or this year. So this P chapter, that's the prerequisites, so that would be pre-cal stuff. And then starting in chapter 1, we did continuity, vertical asymptotes, differentiability, or just taking the derivatives in chapter 2. Extremes in chapter 3, concavity, points of inflection, horizontal asymptotes, and limits at infinity. So we have all this stuff that we have done. So let's really quickly walk through how would we find these things. All right, so x and y intercept, that is a pre-cal concept, right? X-intercept happens when y equals 0, and y-intercept happens when x equals 0. Now remember, x-intercepts cannot be anything else. So I say that because remember, if you have a hole, that'll be a 0 on the top of your rational, but it cannot also be an x-intercept, right? So if it has been accounted for somewhere else, it can't be one of these, if that makes sense. Symmetry. Symmetry is something that we talked a little bit about in pre-cal, where if you plug in like a negative x, and it's the same value, then it's symmetric to the y. If you plug in negative y and it's symmetric to the x. If you can plug in a negative x and a negative y, it's symmetric to the origin. So we talked a little bit about symmetry. Domain and range, that's what x values can I have, what y values can I have. So when we look at domain and range, we are going to think about, is it discontinuous anywhere? This is where you would figure out if you have maybe situations that cause problems in your graph. And that leads to your continuity. Because if you have a problem in your domain, x cannot be this, it's probably because it's discontinuous there. And so domain and continuity kind of go hand in hand a little bit, right? Which leads to the next thing, vertical asymptotes. And so for vertical asymptotes, this is where my denominator equals 0 and it does not cancel. And remember, if it cancels, what is it? If the denominator cancels, it's a hole, which is part of your discontinuity. So holes are where your denominator equals 0 and it cancels, right? And so holes and vertical asymptotes, those help you. Differentiability, this is your first derivative. Can it be derived? Can we take a first derivative? First derivatives help us a couple ways, all right? First derivatives help us with increasing and decreasing, right? They also help us with extremes, but we can do extremes another way too. We can do extremes using concavity. Concavity is second derivative, and those also help us with extremes. So we can use increasing and decreasing to figure out if we have something like that, or we can use concavity. And remember, your extremes will typically happen at a critical point. And so critical points come from our first derivative as well. Our critical numbers come from there as well. Points of inflection, that is second derivative. That's what you get from concavity, right? Concavity tells us points of inflection. Horizontal asymptotes, this is actually something we could have done in pre-cal, right? We could have done horizontal asymptotes in pre-cal. These are our shortcuts. If my denominator has a larger degree, then it's 0. If they're the same, then it's my coefficients. And then limits at infinity, here we have, if it's larger, then we're going to shoot off to positive or negative infinity. So that's what we just talked about, really. All right? And so we start putting all of these pieces together, and all of a sudden we can sketch a pretty good picture of what's happening with the graph by doing these pieces. And so what I typically do when I do these is I'm going to find first derivative, I'm going to find second derivative. I'm going to do all my pre-cal things, my intercepts, my vertical asymptotes, my holes, my horizontal asymptotes. I'm going to do all of those pieces as well. And then I'm going to say, what do I need to use for my first and second derivative that will help me figure out what's going on? All right? And so when you have a sketching of the graph, it's going to ask for a whole bunch of things. And so when you have a quiz on something like sketching a graph, it's going to be a pretty short quiz because you can't do 15 of these problems, right? This would take forever, okay? So looking at this example, I'm going to do a couple things. Usually the first thing I do is I factor it as much as possible, okay? Because I want to see when I start getting into these discontinuities and all this pre-cal stuff, the factoring is going to help me. Now, when I do derivatives, factoring doesn't really help me that much. But when I do pre-cal stuff, the factoring is really one of the first things that I do. So I will factor this guy first. I'll leave that 2 out there. The x squared minus 9 is x plus 3, x minus 3. And on the bottom, I have x plus 2, x minus 2. So I'm just going to leave that out there for the things that I need to use that for. And then I also have the other one for what I would use that particular one for. And I will say this, taking derivatives is easier without the factoring. So in this case, you may want to actually write another one over here and say, well, this is also 2x squared minus 18 over x squared minus 4. Because that's going to help you see your like horizontal asymptote a little bit better, right? Versus the other way. So sometimes you want to see it multiple ways before you actually get started. So let's talk about the pre-cal stuff first. All right, so pre-cal stuff would be your x-intercept and your y-intercept. Okay. We also would be able to do holes and vertical asymptotes. Those actually come from the same things, right? Holes and vertical come from your denominator, all right? Really, we'll talk about horizontal because that's technically a limit theory, but really we could have done horizontal before as well, right? And so horizontal is something that we could have done in our pre-cal world. All of those things you should have been able to do prior to walking in the door, right? And then we start talking about calculus stuff. And so now we have this line in the sand where we have exhausted our abilities in pre-cal world. And we say, well, what can we figure out in calculus? Well, in calculus, we're going to need to take the first derivative because that's going to help us with critical numbers. And second derivative is going to help us with concavity. All right. And so we will be doing first derivative and we will be doing second derivative to see how our calculus world helps us as well. So let's do the pre-cal first. X-intercept. X-intercept is where your numerator is 0, but it doesn't cancel with anything. So I actually have 2 places, right? 2 places where it's going to cross my x-axis. What are those 2 places? Where my numerator is 0, but it doesn't cancel. 3 and negative 3. So my x-intercepts happen at 3, 0, and at negative 3, 0. My y-intercept happens when I plug a 0 in for x. So I do have a y-intercept as well. What's my y-intercept? When I plug in a 0, I get negative 18 on the top and negative 4 on the bottom. So negative 18 over negative 4 reduces to 9 halves, positive 9 halves, right? So my y-intercept is going to be when x is 0, y is 9 halves, so 4 1/2.
How do you know where to plug it?
All right, let's look at our asymptotes here and our holes, our vertical. This is where, my holes is where the denominator cancels, right? It's 0 but cancels. I actually don't have a hole in this one, right? I do not have a hole in this one. So none for this guy. Vertical is where my denominator is 0 but does not cancel. This is a vertical line. So that is x equals 2 and x equals negative 2. I'm going to have 2 of those. Denominator is 0 but does not cancel. And then horizontal is technically my limit at infinity, okay? So when you see limits at infinity, you are looking for horizontal asymptotes, right? Now here's the thing. If it is one of your easy ones, denominator is bigger, that's 0. It's the same like here, coefficients. But if you're looking at what happens as it goes towards infinity, right? Let's say your numerator is larger and it's going to be infinite. you have to consider the positive infinity side of it and the negative infinity side of it, because they may be different, right? We just saw that on the square root one, right? So when you plug in a negative infinity, that's what's happening as x goes towards negative infinity, right? If you have a positive infinity, it's what the graph is doing as it moves towards positive infinity. So you have to make sure that when you do these horizontal, if it's not one of your easy zero or coefficient, and it ends up being infinite, you have to figure out in the graph, okay, my numerator's larger, so I know it's going to move towards infinity, but now I have to consider positive and negative, right? I have to consider what happens as x moves towards the positive and as x moves towards the negative. Okay, in this case, it's a coefficient, so it's going to make our lives a little bit easier, but you do have to think about that. So horizontals, my shortcuts. This is also limits at infinity. So when you see that listed, that's the same thing. All right? So what is it? Well, they're the same. X squared over x squared. It's 2 over 1. So this is a horizontal at y equals 2. Y equals 2. Now, me personally, I would go ahead and graph this piece of it. That's what I would do. I would graph this, and then I would start figuring out what's going on as far as increasing and decreasing.
Because it was the
Shortcut. So we have squared over squared. So we're using our coefficients. And so if you want to, you can go ahead and graph these pieces. We have a vertical asymptote at 2 and negative 2, and a horizontal at positive 2. So we can go ahead and graph these pieces if we want to. We can graph our horizontal, that's my y. We can graph our verticals, that's my x pieces. And then we can graph, we don't have any holes, so we don't have to worry about that, but we can actually pop our intercepts in if we want to. All right, so we have all of these. And then plug these in. It crosses at positive 3 on the x, at negative 3 on the x, and at 4.5 or so on the y. All right. Now let's look at derivatives. All right, first derivative is going to be your quotient rule. So we have 4x times x squared minus 4 minus 2x times 2x squared minus 18 all over x squared minus 4 quantity squared. And of course we will simplify that. So we have 4x cubed minus 16x minus 4x cubed plus 36x. They were kind of nice to us. X squared minus 4. My 4x cubes cancel out, so I end up with 20x over x squared minus 4 quantity squared. All right, so that's my first derivative. How does first derivative help me? Well, I am going to have some critical numbers here, right? Clearly, I have critical numbers. I have a critical number that happens at 0, right? Does everybody see that? Why do I have a critical number at 0? Well, that's where first derivative equals 0. So one of my critical numbers happens at x equals 0. What does that tell me? Well, that tells me that my graph turns when x equals 0. Well, what point happens when x equals 0? Well, my y-intercept actually happens, right? When x equals 0. So if I set my first derivative equal to 0, I get critical numbers. That's where my graph turns, remember? Right? That's where you have a horizontal slope, right, of 0, tangent line, slope of the tangent line. So I actually know that this guy right here is going to be a peak or a valley. Everybody see that? That's going to be a peak or a valley. How do I know that? Well, because there's a critical number that happens there. My graph is going to turn here because this is where x equals 0. The other place is at 2 and negative 2. Those are considered critical numbers as well, right? I don't have a peak or valley there. How do I know I don't have a peak or valley at 2 and negative 2? Because I've already accounted for 2 and negative 2. What are they? They're vertical asymptotes. So I know they actually don't turn there. That's actually where it's undefined. So my derivative is actually undefined on this particular graph, the same place where my original function was undefined. Okay? So I know I may change directions, increasing and decreasing here, but I definitely don't have anything going on here because they're not part of the graph. They're excluded from my domain. But I do know when x is 0, I have a critical number. So if I set the numerator equal to 0, that's a critical number, right? And I already know what the graph does at 0 because I've already done that. When x equals 0, my y is 9/2. So this tells me this point right here is going to be a turn. It's going to turn there. I just need to figure out, is it concave up or down there? All right. So we're going to do second derivative. Second derivative is going to tell us concavity. All right. And so if I do second derivative, I'm going to get my 20 times my x squared minus 4 quantity squared minus, and I get this 40x because I'm multiplying the 2 over times the 2x times the x squared minus 4 to the first power all over x squared minus 4 to the fourth power. I can take out one of my x squared minus 4s, right? You can see that. This guy comes out, one of those comes out, one of those comes out. So I get 20x squared minus 80 minus 80x squared. Is that what that is? Yes. They pulled a 20 out, I think. Yeah, they pulled a negative 20 out is what they did. I'm pretty sure. 20x squared minus 4 squared minus 40x 2x x squared minus 4. Yep, that's what they did. So we get negative 60, negative 80, and they actually pulled out a negative 20 out of this guy, which is where they got the 3x squared minus 4 on top, and we still have our x squared minus 4 quantity cubed on bottom. I'm going to scoot him over. Oh, he's attached now. I'll rewrite it over here for you. So my second derivative looks like this. Negative 20, 3x squared minus 4 over x squared minus 4 quantity cubed. All right. Does everybody see what I did? I just combined, this is all over that little group there. We just combined the 20 and the 80, that's negative 60, right? Negative 60, they pulled out a negative 20, that's where we got the 3. 80, they pulled out a 20, that's where we got the 4. Okay. Make sense? All right. And it's a plus 4, by the way.
This is a lot of work to do before you get around.
All right. Now, here's the thing. All we have to do really is figure out concavity. All right? Concavity. So if I want to figure out concavity, I am just going to plug these numbers into my second derivative. So you can set up increasing and decreasing intervals if you want, but think about your second derivative test, okay? Think about your second derivative test. I really need to figure out if this guy is concave up or down here, concave up or down here, and concave up or down here, right? And I will know what's happening with my graph. Does that make sense? Do you understand? Yes? So if it's concave up, it's possible that this is not, that it comes back down to, like something happens here. Concave up or down here is going to determine if I go up or if I go down here. Because remember, you can cross a horizontal asymptote. That's what happens at the end of it, right? So I just need to figure out my concavity. Well, I can use second derivative test to do that. I can actually take these 3 points and plug them into my second derivative and just figure out if it's positive or negative, right? So let's start here, -3. All right, I'm going to put a -3 in here. So I'm going to pull somewhere else. We'll just do our second derivative test here. So second derivative test for -3. So second derivative test for -3, that's this point here. Well, 3x squared plus 4 is always going to be positive, yes? So 3x squared plus 4, this piece is going to be positive. This piece is going to be negative. So my numerator is negative, always. I don't have to worry about that. My numerator is always negative. Yes, I have a negative times something that's always going to be positive. So we just have to worry about the denominator. -3 squared minus 4, right? What happens there?
Positive 21 cubed.
It's positive 21 cubed. So my denominator is positive. So my numerator is always negative. When I plug in a negative down here, I get a positive, right? So it's negative over positive. When I'm at -3, am I concave up or down? Down, because I am negative. So that actually tells me this guy is going to be concave, if I can draw it. Concave down this whole time, right? Concave down. I know I don't have any other turns. How do I know that? If I had another turn, I would have another critical number, wouldn't I? If I had another turn in the graph where it changed concavity, I would have some sort of critical number because it would be a peak or a valley of a roller coaster, right? I don't have another peak or valley. I only had one. It happens at 0, right? So now I need to figure out, is it concave up or down here? Is this a max or min? So what am I going to do? I'm going to plug it in, right? Second derivative at 0. What happens? Well, my numerator is always negative, right? We already determined that. The denominator, if I do 0 minus 4 and cube it, is that negative or positive? So I have a negative over a negative. Is it concave up or down at 0? It's concave up. So that tells me this guy cannot touch those vertical asymptotes. I do not have another turn, or I would have had another critical number in there. So he has to look like that. There's only one turn.
You said it was negative over negative.
Yeah, negative over negative if I plugged in a 0. This is always negative, right? Because this is positive, that's negative. So this is always negative. 0 minus 4 is negative, and I cube a negative. Negative over negative. And then we're going to test the other side. What happens at +3? Well, at +3, same thing is going to happen at -3, really, because it's a square on the bottom. My numerator is still going to be negative, right? Because I can't make this guy negative if I tried. So I have a negative times a positive up here, negative. I have a +9 minus 4 cubed. Is that positive or negative? So I have a negative over a positive. Is it concave up or down? Concave down. So this guy is going to also be down. He's going to look like a bowl that is down. So he's going to look like that. If you did your increasing and decreasing, you would find that from negative infinity to -2 is continually decreasing. From -2 to 0 is decreasing. From 0 to 2 is increasing. And from 2 to infinity is increasing. So if you did your increasing, decreasing, you would get the same thing. So if you had not had these points to test, you could just pick a point and test it, right? On either side of your asymptote if you needed to. They just kind of gave us ones that we could test because we had some intercepts here. If you didn't have intercepts, you could just pick a point and say, is it concave up or down here? Because I know there's no turn or I would have a critical number. Or if you have a critical number, then you need to figure out, is it concave up or down at that critical number, so I know if I'm coming towards it and turning like we did for that center point. Make sense?